why do we think quantum computing is actually going to allow us to solve some of these problems we can't solve classically, right? So it boils down to two fundamentally quantum effects. One of the effects is superposition. So classical information is basically a string of zeros and ones. Everything that classical computing has enabled is, boiled down to a sequence of zeros and ones. So quantum computing or quantum information has this property that the states can exist in a superposition of 0 and 1, right? So not just 0, not just 1, but a superposition of 0 and 1, right? And you can also have complex superpositions of 0 and 1. So you start to be able to explore a much richer set of states. So if 1 qubit can be in a superposition of 2 states, then 2 qubits can be in a superposition of 4 states, and 3 qubits can be in a superposition of 8 states. So the possibility space you can explore is much more interesting and complex in quantum information. So the diagram on the right is showing you a superposition of 5 qubits, right? So you can be in a superposition of 32 states. So superposition is the first thing. The second thing is entanglement. This idea of entanglement is, okay, I've got 2 qubits and I'm entangling them together. So measuring the first qubit can tell me something about what will happen when I measure the second qubit. Okay, so entanglement is the second property that gives quantum information a really unique difference. So together, this allows us to totally change how we run algorithms, right? So take the optimization case. If I'm going to consider 3.6 million possible ways of configuring 10 people at a table, classically I have to consider each one individually, and then I have to compare them all, right? Here's how quantum computing is going to solve that problem. You take your qubits, you go into a superposition of all the possible states, all the possible configurations, and then when you encode the problem into your quantum computer, you're applying a phase on each of the states. The phase is, that kind of axis towards the center of that sphere you saw in the previous chart. You encode a phase on each of the states. And when waves are in phase, the amplitudes add. And when waves are out of phase, they cancel, right? So when you have noise-canceling headphones, what you're doing is you're creating noise that's exactly out of phase with the noise you're trying to cancel, right? So in quantum computing, you're going to go into a superposition of all these states. When you encode the problem onto the machine, you're applying a phase on each of the states. And then you're using interference. And you amplify some answers, and you cancel other answers. Eventually, you arrive at the solution. So it's just totally different, right? You just got to completely rethink how we're going to solve these problems, and that's kind of how quantum's going to do it. So it's obvious why the number of qubits matter, right? If I have 1 qubit, I can be in 2 states, and the more qubits I can have, I can be in a superposition of 2 to the n states. But another important factor is this error rate, right? I have to be able to control what's going on in the qubits. If I have really high errors and all of my operations don't work out as I expect them to, then that's not going to really work. So we're promoting a new metric called quantum volume, where we're saying, okay, if you increase the number of qubits, you can get to higher computational power, but not if you have really high error rates. So we have to both move towards lower error rates and higher qubit count, okay? So how do you actually build a quantum computer, right? This is how it should work theoretically. How do you actually go and do this in real life? So first of all, you have to have qubits that work in such a way that you can harness quantum mechanics. So we build basically artificial atoms. Atoms behave quantum mechanically. We build an artificial atom, and we make it out of a superconducting Josephson junction coupled to a microwave resonator. Okay, so this is what it actually looks like on the chip. You have these squares that are your qubits, and these squiggly lines are your microwave resonators, and inside of the qubit is a superconducting Josephson junction. And we got to cool this thing down to 0.015 Kelvin, where 0 is absolute 0, right? Room temperature is 300. This is significantly colder than outer space. And we talk to the qubits with microwaves. So this is what it actually looks like. This is how we talk to the qubits. We have inside of a dilution refrigerator, which you'll see on the next chart, we have all of these microwave cables that allow you to actually go and probe the qubits with microwaves, okay? And this is what it looks like in the actual lab. So these giant white cylinders, these are our dilution refrigerators. And here you can see my friend Nick working on one of the insides of the quantum computer.